First, thanks for inviting me for this talk. And today I will present one of my PhD's work working on the physics-based and data-driven models for process microstructure and mechanical properties in metal additive manufacturing. Before introducing my research, I want to introduce myself first. I'm now a postdoc at Stanford and working on an experiment project to use a dark field X-ray microscopy to visualize the malput dynamics in metal additive manufacturing, and also combined with the theory to try to resolve the defects problem. And before that, I got my PhD from Northwestern University, and I developed models and simulations for the malput dynamics and also microstructure evolution in metal additive manufacturing. And before that, I got my master and bachelor from China University of Petroleum. Metal additive manufacturing is a process to build parts layer by layer. It has been applied in many areas, and it has many advantages over traditional techniques. For example, we can use light material and can build the parts with lightweight, and we can design the samples and parts with complex geometry, and people also can customize the parts. Now it has been applied in aerospace, automotive, medical devices, and also surgery implants. There are mainly two processes in metal additive manufacturing. One is a powder bed diffusion process. In this process, powder will be spread in a very thin layer, and then we use a laser to melt the material. Actually, that involves multi-physical and multi-scale problems. For example, when we use the laser to melt the material, when the temperature increasing and above the melting temperature, the solid metal will turn into the liquid. So that involves free flow and also convection, conduction, and radiation. When the temperature is still increasing and some of the particles will evaporate, that will also involve the vapor flow and the interaction between the laser and the material. When we remove the laser, temperature will become decreased, and some part of the material will cool down and become solidified. That will also involve the phase change and also solidification. There's another process which is called the direct energy deposition. Actually, this process are very similar with the powder bed diffusion, and it involves a similar physical phenomenon. But the difference is that in the DED, we use the powder will be deposited from a nozzle, and it will be melted by laser at the same time from the deposition. There are multiple scales in metal 3D printing, from the micron scale to the meter scale. For example, the metal powder itself are actually in the micron scale. Usually the average of the powder size will be 50 micron size. And we also look at the microstructure from the experiment. They are also in the micron scale. And the major part of the microstructure can also extend into the millimeter scale. Sometimes we also simulate the malput dynamics with the heat transfer inside the malput. That is usually the millimeter scale. When we go above, we also want to simulate the whole parts for the dynamics. And that is will go into the meter scale. And also the properties will also in the part scale. However, there are many challenges in metal additive manufacturing. For example, the printable materials are very limited. That means that not all metal alloys can be left in metal additive manufacturing, since some will not print with perfect mechanical properties. And also that there will be some defects formed during the process. For example, the lack of fusion, gas porosity, and also cracking. As we can see that in this figure, there are some very irregular dark pores occur. That is due to some of the metal are not fully melted. So that is because of the lack of fusion. And there are also some very small pore and with regular and spherical shape. And we can also see in this figure. So that is because some of the gas are entrapped, and that will form the pores. That is more like the porosity. And we can also see that there are some cracks forming both in the macron and the macro scale. That's all of them are defects. Another challenge is to develop the correlation between the process structure and the properties. And I will introduce this in later slides. As we can see that during the process, different laser parameters and tool paths will lead to a very complex thermal process with the dynamics and in free flow in the metal additive manufacturing. And different temperature field will lead to different solidification process and will change the microstructure formation. And the microstructure will also affect the mechanical properties. Here is an example from the literature and from this paper. This is several samples built by the DED process, and the material is stainless steel. As we can see, we can look at some locations from the samples and look at the microstructure. So at the bottom, the right-hand side one is a BSD microstructure for the case of with high power, while the left one is a microstructure for the low power case. We can see that the microstructure for the high power has much larger grain size than the low power case. When we look at the stress and strain curve, you can also see that the lower power case has much higher strength than the high power case. That actually this explains that different laser parameters and the process will change microstructure formation, and different microstructure will have different mechanical properties. However, that is not very fully understood. And for this work, first I will introduce the simulations of the DED parts, and then we will use experiment to validate our simulation results. And we analyze the correlation between the temperature microstructure and the mechanical properties. And then later on, we use a data-driven model to predict the mechanical properties from thermal histories. And first, I will introduce the framework of these data-driven models of the process structure and properties. First, we did the additive manufacturing experiments, and we vary the different domain size and also dual times, but with the same laser parameters. And we built for 3 different cases of the thin walls. At the same time, we can see that we use an IR camera to measure the intensity. That intensity is related with the temperature. And after build, we did the tensile test to measure the mechanical properties, such as the strength, yield stress, and UTS and modulus. And we also took small samples from the built parts and did SEM to look at the microstructure. We developed the thermal models to simulate the temperature field for this whole process. And we use the IR measure data to validate our simulation results. In order to analyze the correlation between the process with the property, we calculate the cooling rate and also the defecation rate from the thermal models. And we and also compare the information from the thermal to the microstructure and the mechanical properties. But we found that the correlation between the strength with the cooling rates are not perfect. And then we did use machine learning ways. We develop a 1D convolutional neural network to try to resolve this problem. And the input of this is the thermal history and we try to predict the mechanical properties from the temperature. So for example, we can predict the ultimate tensile strength, yield stress, failure stress, and modulus. And in the end, we got pretty good results. First, I will introduce the simulation models. And first, we develop a FEM-based model for the part-scale DD simulation. And this is actually run for parallel computing and designed for large-scale additive manufacturing builds. The right figure shows the geometry and the mesh. The top part is a mesh for the thin walls, while the bottom part is for the substrate. And the left one is the simulation results. And we build this layer for about 120 layers. The material is about Inconel 625. As I talked before, we simulate the cases for 3 different cases with the same laser parameter, but with different dimension and also dwell times. The dwell times means that how many time you stop at the end of the laser scan and before the next scan pass. In order to validate our simulation results, we compare the measured IR temperature data with our simulation. We choose some specific locations from the thin wall and look at the temperature history. The solid line are the temperature history for simulation, while the dashed line are for the experiment. And we can see that for most part, actually the simulation agrees pretty well with experiment, but actually there are some discrepancy during the first parts. That is actually because the IR camera are only measure the intensity instead of temperature, and the intensity of the liquid state are actually much lower than the solid state. That's reduced that we measure the data very low at the melted area. So actually in that area, the temperature is pretty high. So because that, we only compare the data after the melting temperature. And it looks pretty good agreements. Except for one location, we also extract multiple locations from different cases and compare the simulation results with experiments, and they all have the similar trends. At the same time, we did the SEM experiment to look at the microstructure from different walls. For example, from the left to the right, these are different cases. The top 3 figures shows the microstructure from the side view, while the bottom 3 figures shows the microstructure from the top view. The top view is actually is normal to the building direction. In each figure, so the large gray area represents the major gamma matrix, while there are some small white area that is actually the left faces. Inside of some white area, there are small dark spots that is actually the delta faces. Both the lefts and the delta faces are detrimental to the mechanical properties. We compare the microstructure results and also measure the grain size and compare with the mechanical properties. And then we find like from the case A to case C, the grains are become finer and with higher strength. We continue to look more data, and for this case, we measure we calculate the cooling rate from the simulation temperature data, and we also calculate the and analyze the primary dendrite arm spacing and the left faces fraction from the experimental XEM images. And we compare those information with the mechanical properties from the tensor test. We can see that from the case A to the case C, the cooling rate is increasing, and also mechanical properties also increase. And then we move on, we want to look at this similar comparison instead of from different cases, but from the same cases from different locations in one thin wall. As we can see that point 1 is very at the top part, and point 8 is at the middle part, while the point 12 is at the bottom part of one built samples. And we compare the cooling rate and also microstructure and also mechanical properties for this comparison. And from the top to the bottom part, the cooling rate is decreasing, while the mechanical properties are actually not linear correlated with the cooling rate. In order to analyze the correlation between the cooling rate and the UTS, we actually compare the data for the other locations and from different samples. The different marks in this figure shows the different cases, while each data are actually from different locations measured from the experiment and also from the simulation. And we generally we can see that there is a trend with increasing cooling rates with the strength, but actually we use a linear fit to fit this. The R2 square is only 0.3. That indicates that the correlation between the cooling rate and the UTS is not perfect. And it means that maybe the solidification cooling rate alone is not sufficient to predict the properties. Instead of comparing the cooling rates is actually like a self-defined features from the temperature history. And we use a convolutional neural network to try to automatically detect the essential features from the temperature. And we want to correlate the temperature features with the mechanical properties. And here in this slides, we show the architecture of the convolutional neural network. And the input of this architecture is simulated some history for different cases and also locations. And the output is or mechanical properties. For the architecture, we use 3 different convolutional layers and 2 connected layers. This slide shows our prediction results. So we can see that we compare the mechanical properties for UTS, U-stress, failure stress, and modulus. For most of them, for example, from the UTS to the failure stress, we have pretty good agreement from the prediction with the measured data. Well, for the modulus, we can see that although it also agrees good, but the R2 square error is not very high. That means that the prediction is not matches pretty well with the experiment. So actually, this is within our expectation. That is because the modulus is the mechanical properties related with the material itself instead of the process parameters. In order to interpret the prediction results from the neural network, we visualize the convolutional layer features for each convolutional layer. And the top 3 figures shows the plot the extracted features from each channels of different layer. And I will introduce one of them. So for example, here, this shows about 32 extract the features from the 32 filters from the first convolutional layer. And when we zoom in, so we can see that the blue line are actually the extracted features. The red line are the extracted features. And in order to analyze this, we plot these features with the temperature history as the same plot. There are major 2 patterns, and the group 1 is that we can see that there are only some extracted features and data in the first few thermal cycles. And we can see there is also another patterns like the group 2. Instead of only have the data in the first few thermal cycles, they also have a tail and till the end of the cooling period. So we can get a sense that not only the first few thermal cycles of this process matters, but also the whole thermal process will affect the mechanical properties. And also for the tail part from the extracted features, we can also see that this actually period represent the temperature between the 800 to the 100 K. That is actually the temperature that some strengthened precipitates will form. That will also indicate that some precipitates will form, and that will strengthen the material and affect the mechanical properties. In conclusion, we did the thermal model to predict the temperature for the DED parts that agrees well with the experiments. And we use machine learning to extract the dominant features from the thermal history, and that gives a good prediction of the mechanical properties. And from the extracted features from the machine learning, and we can learn that there are some correlation might indicate some physical phenomena. For example, some precipitates will form during the intermediate temperatures. At the end of my talk, I want to acknowledge my PhD advisor, Professor Greg Wagner, and also collaborated professor with Professor Jing Cao and Wenqin Liu, and also my committee members, Professor Wei Chen and Peter Voorhees. And I also would like to thank the collaborators for this paper, Jennifer Glam, Jennifer Bennett, and also Lin Chen, and also the funding agency. Thank you very much, and I will take any questions.